Welcome back. Today, in this video, we're going to take a look at topic 6.7 and 6.8. Very important topics. Talking about the fundamental theorem of calculus and definite integrals, finding antiderivatives and indefinite integrals as well. So let's start with a little activity here. What if we wanted to find f of x, whose derivative is a little f of x equals 3x squared? What would it be? Well, there's not one answer to this. There's actually infinitely many correct answers. So let's write down a few that would work. So maybe f of x would be x cubed, right? Because the derivative of that would be 3x squared. Maybe f of x would be x cubed plus 1, because the derivative of 1 would be 0. So maybe f of x would be x cubed minus 4, because the derivative of negative 4 would be 0. We can go on and on like this, right? But really, sorry, I should be using capital F's for all these. But anyway, really, the point I'm trying to make here is that as long as our base function here is x cubed, we can add any constant we want after this. So we write that by saying plus c, plus some constant. Any function in this form will have a derivative in this form. Okay? The integration symbol is certainly not new to us at this point. We've been using it for a few weeks. Instead of writing what function would have a derivative of f of x, we write an integral symbol of f of x dx, which is read as we've been reading it as the integral of f of x with respect to x. What's different about indefinite integrals is that we don't put bounds on the top and bottom of the integral symbol. Okay? Quick note here. When we wrote this plus c, that's not just me writing a plus c there to show you that. That is mandated that every time we do an antiderivative or an indefinite integral, we write a plus c at the end of it. Okay, if you don't do that, it would not be considered correct. So let's jump right into some basic integration rules. Now remember, integrals are just the opposite of derivatives, right? So the antiderivative or the integral of 0 is just going to be some constant, because the derivative of some constant is 0. The integral of k is going to be kx plus some constant, because the derivative of kx would be k. This third one is this little special rule here. It basically says that we could take a constant that's multiplying a function out in front of that integral. So we can write the integral of kf of x as k times the integral of f of x. All right, 4 and 5 are pretty much the same thing. 4 is just saying if we're adding two integrals together. 5 is saying if we're subtracting two integrals. We could break those integrals apart. And 6, this is probably the most important integral rule. It's kind of like the power rule for integrals. So remember, the power rule for derivatives is we would bring the exponent down and then lower the exponent by 1, right? But for integrals, what we do is we add 1 to the exponents, and then we divide by that new number. And then don't forget to put plus c at the end of it. Okay? This works for any power n that is not negative 1. You'll see what we do if it is negative 1 later on in this section. All right, we're going to jump right into some antiderivatives, all right, or indefinite integrals. They mean the same thing. Either way, we're trying to find the antiderivative of the function. So we have 3x, which we don't need to do this, but maybe for right now, we want to write it like this just to kind of see what we're doing here. We use the power rule on this. So this would be 3 times x squared over 2 plus c. Now we can simply write that as 3x squared over 2 plus c. All right, and an easy way to check if you're right at this point is to just take the derivative of this and see if you get back 3x. For part B, so here's a kind of a one that a lot of students tend to mess up a lot because they see the x to the third and they just want to use the power rule on that. You can't do that. You can't use the power rule with something in the denominator like that. But what you can do is rewrite it so now that it's in the numerator. And now we can use the power rule on that. So if we raise the power by 1 and divide by that new number, we get our answer that looks like that. Now, we don't want our answer to look like that when we're done. We don't like the negative exponent there. So we can rewrite our answer as negative 1 over 2x squared plus c. Part C may not look like it, but this is just another power rule problem as well. Okay, what we want to do first is change this to an exponent, just like we did when we did derivatives. We want that to be an exponent. So when we take our antiderivative, we raise that power by 1, so adding 1 to that, we get 3/2, and then we divide by that new power. We never want to leave a fraction inside of a fraction like that, so we want to rewrite that as 2x to the 3/2 over 3 plus c. So that's just taking the reciprocal. If you go back to your Algebra 1 days, if you had a over b over c over d, that's the same thing as saying a over b times d over c, right? So all we're doing is we're taking this and multiplying by the reciprocal, which is 2/3. Part D. Okay, just like when doing derivatives, you can't just take the derivative of each of these pieces and think that's your answer. The antiderivative of each of these pieces and think that's your answer. Okay? Unfortunately, for integrals, for antiderivatives, there is no power rule. So we cannot do this the way it is currently set up. But what we can do is we can rewrite this. Well, first of all, let's rewrite this as x to the 1/3 times x minus 4. And now what we can do is we can distribute that x to the 1/3 in. So this becomes the integral of x to the 4/3 minus 4x to the 1/3. And now we can take the antiderivative of both of these parts individually. So this would be x to the 7/3 over 7/3 minus 4x to the 4/3 over 4/3 plus c. Rewriting that, we get 3x to the 7/3 over 7 minus 3x to the 4/3 over, so the 4 but end up canceling themselves out there, plus c. And that would be our antiderivative to part D. Part E, just like there is no product rule for antiderivatives, there's no quotient rule for antiderivatives. So we cannot take the antiderivative the way this is currently written. But what we can do, again, is we can rewrite this. First of all, we can rewrite it as x plus 1 over x to the 1/2 dx. And then we can rewrite it as x over x to the 1/2 plus 1 over x to the 1/2 dx. And finally, we can rewrite it as x to the 1/2 plus x to the negative 1/2 dx. And now we can rewrite this, or now we can take the antiderivative of this as x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 plus c. And rewriting that, we get 2x to the 3/2 over 3 plus 2x to the 1/2 over 1 plus c. Just like there's no product and quotient rule, there's also no chain rule. So we cannot take an antiderivative of something that looks like this either. But what we can do, again, is rewrite it. So we can rewrite this as t squared plus 1 times t squared plus 1. Now that does not actually help us. But now we can FOIL or distribute to get t to the 4th plus t squared, or plus 2t squared plus 1. And now we can use our power rule. T to the 5th over 5 plus 2t to the 3rd over 3 plus 1t plus c. Example 2, given that f double prime of x equals 3, f prime of 2 equals 5, and f of 2 equals 10, find f of x. Okay, so basically this is going to be a double integral problem. We know that f double prime of x equals 3. So if we were going to take the integral of both sides of that problem, well, the antiderivative of f double prime is just f prime. The antiderivative of 3 is 3x, but don't forget the plus c. And we know right here that f prime of 2 equals 5. So now we can put 2 comma 5 into that equation. So 5 equals 3 times 2 plus c. 5 equals 6 plus c. Negative 1 equals c. So now I could say that f prime of x equals 3x minus 1. And if I repeat that process, so if I take the antiderivative of f prime of x dx equal the antiderivative of 3x minus 1 dx, I would get f of x equals 3x squared over 2 minus x plus c. And I know the point 2 comma 10 is on f. So 10 equals, if I put 2 into that, I would get 3 times 4 over 2 minus 2 plus c, which is 12 over 2, which is 6. So 6 minus 2, which is 4 plus c, or c is 6. So our final answer here for f would be 3x squared over 2 minus x plus 6. Let's look at a couple other rules as well here. How about the integration of some trig functions that we know the derivatives of? Well, to do this first one, you want to think, what function has a derivative that's cosine? So the antiderivative of cosine would be sine. What function has a derivative that is sine? Be careful there, it's not just cosine, it's the opposite of cosine. Some other rules that we hopefully know. What function has a derivative that is cosecant squared? That would be negative cotangent. What function has a derivative that's secant squared? That would be tangent. What function has a derivative that's cosecant cotangent? That's negative cosecant. And what function has a derivative that's secant tangent? That would be secant. Hopefully you remember those derivative rules from first semester. Okay, what you might not notice here is we don't have an integral for secant, we don't have an integral for tangent, we don't have an integral for cotangent or cosecant. We will learn those. They're a little bit more complicated though than what we see here. All right, so example 4, find the following antiderivatives. The integral of 2 sine x dx. So remember, that's just saying that we can think of it as 2 integral of sine x dx. You don't have to do that, but it might help you see it. And that would be negative 2 cosine x plus c. And again, easy way to check this take the derivative of this and see if you get 2 sine x back. Question B. All right, we know that there's no quotient rule for antiderivative, so we can't take the antiderivative like this. Okay, it's just not possible. But, as always, we can rewrite this. We can think of this as sine over cosine times 1 over cosine. Well, how's that going to help? Well, sine over cosine is tangent, and 1 over cosine is secant. And we know the integral of tangent secant is secant. So that's going to be secant x plus c. We will use those much, much more as we go throughout these next couple of chapters. Example 5, now we're talking about exponential functions, all right? Remember how we had the derivative of e to the x was e to the x? Well, guess what? The antiderivative of e to the x is e to the x. We love that e to the x function, right? So find the antiderivative of 5e to the x. That's just going to be 5e to the x plus c. What if the base is not e? Okay, so that's just going to be a to the x times 1 over natural log a. Or you can say divided by natural log a. Either way. So the antiderivative of 6 to the x is going to be 6 to the x over natural log 6 plus c. Technically, we did that for this one as well. It was just e to the x over natural log e. But since natural log of e is 1, we don't have to write that. And that's why it's a little bit different for base e than for any other base. All right, one more rule. The antidifferentiation of 1 over x. This is one that will be used a lot. So remember all the way back in the beginning when we did the power rule. Let's go back there. We said it doesn't work if n is -1, right? So in this case, remember that 1 over x is the same thing as x to the negative first, right? These being exactly the same thing. So if we are taking the antiderivative of 1 over x, we cannot use the power rule. Instead, the antiderivative of 1 over x is natural log of the absolute value of x. We have to say absolute value because remember, we're not allowed to take logs of negative numbers, okay? So in theory, this is a very simple rule to follow. Sometimes it can get a little bit complicated when we get a little bit deeper into these antiderivatives. But for this one, it just says find the antiderivative of 5 over x. You can think of it as 5 times the integral of 1 over x, or you don't have to think of it that way. Either way, the answer is going to be 5 times ln the absolute value of x plus c. Okay, we're going to stop this video here. We're going to say that this is going to be the part 1 of these notes. The next video, we'll do part 2. We'll finish up the last 2 slides of these notes. All right, hope to see you back here to check out that video. Thanks for checking in today.